do vacuum tubes. All right, so now we know about amplifier classes, and you know from previous classes how to build amplifiers with transistors or excuse me, BJTs and MOSFETs and that kind of thing. Let's talk about tubes, and then we'll look at how we do some tube circuits. So basic, what are tubes? Well, they're these
Valves, yeah.
valves. Yeah, that's the British term, right? And in some sense, it kind of makes sense. The idea with, I'm not 100% sure where tubes come from. I always thought it was because they look like they're a little glass tube, kind of like a test tube, right? They're inverted. Valve makes sense, you know, from how do we always do an analogy of electrical current? We talk about water flow, right? High current is lots of water. They're all the same thing. It's current. You reduce the pipe size, reduce the resistance. Well, valves allow you to shut it on and off, and that's what tubes do. And you know, it's kind of interesting to think about. I remember, like when I was a student in the late '90s, there was a discussion about, you know, what was the biggest invention of the last century. And I think everybody, I think there's IEEE had an article on it, and the agreement was the transistor. And it's kind of an interesting one because the transistor wasn't the first controlling device. Tubes did that. But it was what led to the integrated circuit. You couldn't have an integrated circuit without transistors first. You couldn't you couldn't create a CPU. You know, that level of integration with anything other than the transistor that we know of. So it was key development, but I think it kind of overshadowed tubes because tubes were really the first analog or first fully electronic way of controlling things. Right? You had relays beforehand. You could send current to a relay and have to flip a switch. And there's actually an old book, I'd love to get one, but a friend of mine had an old book on relay logic that you could just do, you know, all the tables you're used to doing with gates, you could do it with relays. And I'd really love to get my hand on it because I think there are ways of applying that to guitar switching, right? Because a lot of the guitar switching stuff is based on existing designs, and some people have been clever and, you know, transpose things that instead of switching the pickup wires to different places, you're switching where hot and ground connect to different pickup wires. And so, you know, by inverting the problem, you get different things. And I'd like to find if there is a mathematical basis for that. I think the relay switching logic techniques might apply there. But tubes got you away from that. Now you can have a circuit without moving parts. You know, and even though we think about tubes burning down and having to replace tubes and less lifespan than transistors, they still last a heck of a lot longer than relays, which constantly, not only moving, but we're arcing. You know, whenever you break a relay, you get a little bit of arc. So tubes were a big advance. And we'll talk a little bit about when they came about in history. But remember, the first computers were vacuum tube based. You know, ENIAC and the very first implementation, I think even some of the very first commercial ones were all tube-based. And you still have tubes in commercial products into the 60s and stuff. That's when you started to see people advertising transistor radios. Transistors were a big thing. You know. And then after that, there are very limited places where tubes were common after that. There were guitar amp, audio amps, high power RF amplifiers, because of the capacitance and the cost. It was cheaper and easier to use tubes for high power, and especially like AM transmitters, really high power stuff. They're often tubes. And there was one more thing that was very common, where it used to be, I could say, that everybody had a vacuum tube in their household, whether they knew it or not. But that, in the past 5 to 10 years, has gone away as well. And that was TVs, yeah, picture tubes. You look at the RCA tube bag, and you're probably half of it was picture tubes, you know, and the inner workings were a little different, but it all came down to controlling electrons flowing through a vacuum. You know. So That's where we're starting to see them less and less. All right, but the basic tube is a bunch of electrical elements enclosed in a glass envelope, and then they draw a vacuum in that glass envelope, right? Because if you have air in there, the electrons flowing through there are going to cause problems. Some tubes are filled with other gases. There's a good exploded diagram of a tube on this first handout from the RCA tube manual. That is a great diagram that kind of shows you the parts. I actually have a 12AX7 that kind of part. Unfortunately, I couldn't find it for the lecture today. But if you look at the 12AX7 here, you can see through the glass, you can see the metal plate. If you pull that back, you can see what's shown in the RCA diagram, these spiral elements that are the grid. And if you look through the grid, you can see the inner part, which is the cathode. We'll talk about what those parts are in a second. Okay, so basically, how do tubes work? What are the underlying physical principles? Now, I'm not going to get into the physics of it all because that's not my strong suit. But roughly, there are a couple things. There are, the first thing is the principle of thermionic emission. So the idea is that when you heat metals, some of the electrons come off the metal, they form a cloud around the metal. So if you think about an incandescent light bulb, it's got an element in it, it's got a heater in there. It's creating a space charge around the filament of electrons. Now it's not doing anything with them. But one of the things that happened when Edison was developing the light bulb is he actually made one, Edison was an experimenter. He did a lot. If he did things once, he did it 100 times, 1,000 times. And one of the designs for the light bulb had the filament, and it was kind of supported by a metal plate. And one of the things he did at some point was put a charge on that plate. And he discovered that if you heat this and you put a positive charge on there, you actually get current flowing across this vacuum. So that was a major thing. But I'm not sure how far he documented, but he really didn't develop anything. Fleming came along, and in 1904, he patented the diode, which is effectively that same thing. It's using the Edison effect for a actual purpose. And now we get to the common terms that we see for a solid state diode, where you've got the solid state diode, you've got the cathode and the anode. The current flows from the anode to the cathode, but it won't flow back the other way. That's how the original diode worked. You had the cathode that was heated, create all these electrons, put a positive charge, you got current. You got the electrons flowing from negative to positive, which is what we call current flowing from positive to negative, of course. And that creates a diode. Then as time went on, they came up with other ways of doing it. They said, well, okay, as you heat the metal, you create this cloud of electrons. But you can heat the metal directly, where your filament gives it off, or you can put the filament inside a sheet of material. So the filament just provides heat, and the cylinder of material around it is what creates the electron source. So the advantage of that, and that's called an indirectly heated cathode. The advantage of that is that you tie this tube of material to your ground, that's your signal, and you've got this heater inside that's isolated. And most tubes we deal with are indirectly heated. It allows AC noise to be dissipated, and then it also allows for close spacing and shared heater elements, right? Because now you can use the same heater element to heat multiple tubes, and they're electrically isolated. So that's an advantage. Direct heating, though, it is more efficient, and there are some tubes with direct heating. I don't know if I called out any by name. Okay, but yeah, the basic implementation is shown here. That when your battery is wired this way, you have current flow. When your battery is reversed, you don't, because it's a diode, right? At the core level, it works the same as a solid state diode. It allows current in one direction.